Hi, my name is Doug Santry, and I'm the author of the AI text Demystifying Deep Learning. Today I'm here to show you the generator function from a generative adversarial network that has learned how to fake threes from the MNIST dataset. The generator function is one part of the adversarial network that tries to fake out the discriminator portion of a GAN. For a full description of GANs, please see the linked videos. What you're seeing at the moment is the generator function slowly learning how to draw a three, and it keeps getting closer and closer until finally it converges. Today I'm going to show you how this works, and for those of you familiar with classifying neural networks, this is not going to appear too strange to you. You can really think of it as a classifying neural network, but simply going in the opposite direction, including all the pieces such as convolutions. So as we dive into the heart of the network and we look around, we can see the different layers. As the input signals come in, they change their state. There are a number of different kinds of connections. What we're looking at here may appear to be a spider's web, but actually they're simply point-to-point connections, and there's so many of them that when they're rendered, they appear to make a spider's web of sorts, but they're not. They are point-to-point connections. There are just a great many of them. So as we zoom out and we see the entire network, we can begin to discern the different individual portions of it. And again, for those of you familiar with classifying neural networks or convolutional neural networks, this architecture appears to be quite similar. But whereas a CNN would have an input on the left there, that's actually the output, right? It's the generated image. The generator is trying to generate fake images to fool the discriminator, which is an ordinary classifying neural network. The actual input is here on the right in what would ordinarily be considered the logits. They're not. It's actually just a vector of random noise. It's usually sampled from a uniform distribution or a normal distribution. And its size is not even necessarily related to the output image. So in this example, we have a vector of length 100, which is learning an MNIST data set, which is an image of 28 by 28, which produces a 784 length vector. So the actual sizes don't even necessarily have to be that strongly related. What's actually happening, the important bit here is that next layer, right, which is a fully connected layer of perceptrons. And it's the learned parameters on these edges or connections that actually does all the magic and transfers the noise from the input vector, which is again just randomly sampled noise, and actually tries to produce a recognizable image. Okay, and then once we've actually performed that transformation in the fully connected layer, the next set of layers are transposed convolutions. Now these are just ordinary convolutions, but instead of going in the normal direction, right, which is where we take a map and we apply a kernel to it and subsample it down to a smaller map, we're going in the opposite direction. We're taking a smaller map and building a bigger map, and we're doing that by applying the kernel in the opposite direction, which is why it's known as a transposed convolution. And we do that a number of times, and as you can see, right, we have a 7 by 7, which goes to a 14 by 14, and finally goes up to a 28 by 28, the desired size of the image for an MNIST digit. So again, this should be very familiar for those of you who are familiar with classifying neural networks. It's just going in the opposite direction. And here we are looking at the output, not the input. And that is how generator functions work. This is, of course, a very trivial example because an MNIST image is quite small. Again, for more details, please see the linked video, and I'll explain the loss functions and how the discriminator and the generator compete against one another. Thanks very much.